This is the cylindrical external pressure vessel with stiffening rings. In the design of stiffening ring, there is no direct procedure or formula to size or design the ring. Instead, the specific size and type of ring are first specified, and then they are analyzed for their moment of inertia and resistance against lateral buckling. If these parameters satisfy the design criteria, the ring design is then optimized and finalized. The question is why there is a need of stiffening rings. If the actual external pressure exceeds the maximum pressure the vessel can withstand, then the options for reinforcement include increasing the vessel's thickness, increasing the shell thickness solely to meet external pressure requirements may not always be cost effective. Our second option is to altering its geometry. Geometry of the vessels means the length to diameter ratio and other dimension and shape of the heads, and also vessel's diameter and length cannot be changed easily once designed due to a couple of reasons. The obvious reasons may be the design capacity, position and orientation in plant layout, constraints in instrumentations and operations, cost effectiveness, integration with other equipment, and local machining and fabrication facility constraints for a typical vessel, and also a couple of other reasons may be. So what is the solution? One practical solution is there that the distance between lines of supports can be changed or adjusted. This is an alternative solution for strengthening the vessel against external pressure. To utilize external or internal stiffening ring or a combination of them. But how this actually works? Notice here that reducing the distance between support lines by adding stiffening rings enhances the stability of vessel shell. The effect is similar to a shorter simply supported beam that can withstand greater external loads. It is exactly what the stiffening ring do with external pressure vessel. The required thickness of a shell with a given diameter under a specified external pressure can normally be reduced by shortening the shell's effective length in between the support lines. The length can be reduced by providing stiffening rings at various intervals. Adding stiffening rings also provides an excellent solution in some other stages of design, fabrication and operations. The first one is due to miscalculation in designing the thickness prior to fabrication. In second scenario, it may be possible that some changes have been made in process condition later on of previously installed vessel. The third possibility is that a newly designed vessel has been started and it has been reached up to such a stage of fabrication that you can do nothing with vessel length and diameter. These issues can be solved simply by adding stiffening rings. Let us start the design procedure of the stiffening ring. So where to start? Let us first take some overview of some of the main steps for the design of stiffening rings, and then we will deep dive in each of step. In first step, select or suggest the type of stiffening ring and determine its cross-sectional area AS. So what is the criteria for the selection of stiffening rings? There are different types of stiffening rings. Try to choose any standard stiffening ring available in your local market, but standard stiffening rings create problems in circular bending and fabrication. Then the other way is to choose a flat plate that can be easily bended and welded to the shell, even in small several pieces, and then take more flat plate and make angle, C-channel or whatever you suited, and in this way bending and fabrication become much easier, whatever you suit, but each of them will have different cross-sectional area respectively. Now in the second step, assume the required number of rings and distribute them equally between headlines at 1/3h of its depth of head, between jacketed section, cone to shell junction and terminal dimension LS. We will see all these cases one by one respectively. So first, in case of cylindrical vessel, we are assuming that 4 stiffening rings of T-bar type have been suggested and installed between headlines at 1/3h of its depth of head, as they are acting as a line of supports and shortening the simply supported beam. For the sake of better understanding, it is necessary to discuss the concept of support lines. Support lines are the parts of the vessel contracting the action of external pressure depending on the geometry and movement of inertia of the different elements at